Okay, good afternoon, class. Can you hear me?
Good afternoon, madam. Yes.
Okay, thank you. Let's have a look on your tutorial 7 that you have done in last lesson. Okay, let me check. So, okay, you are working on this structure, and you have provided me the solution, and you have correctly, okay, found your R1. Okay, let us move back to uh, your tutorial question. Okay, so wait. So you have solved for this primary structure M naught, okay, to get the bending function, and then solve for this M1, the redundant structure, wrongly, okay, for the bending function, and then you write the compatibility equation and solve for the R1, okay, which the R1 right now is BY. Okay, so what next then? Okay, so it will be depends on the question. Okay, if the questions request you to determine the remaining of support reaction, so you need to um, uh, determine this according to the request. Okay, or probably ask you to draw the shear force diagram or bending moment diagram. Okay, so right now I will show you what if, okay, you have to determine the remaining of the support reaction after you have determined the redundant force. Okay, so I will show you in my slides. Okay, can you see my slides right now with the table in blue color?
Yes.
Yes.
Okay, so right now I want to show you how to determine the support reactions in the real structure after you determine your R1. Okay, your R1 is 105 kilonewton. Okay, and let's say you want to determine AY. Okay, so AY is here. Okay, you can use this formula M naught plus M1 R1. Okay, I have introduced this formula in your thrust analysis earlier in the flexibility method. If you still remember, we have this N equal to N naught plus N1 R1. Okay, basically these equations are the same, only the forces involved are different. Like for example, for the truss, talk about the axial force, and for the beam, frame, arch, talk about bending moment. Okay, so if you have more redundance, so this equation become longer. Okay, it become N2, R2, and so on. Okay, so now we are going to use this equation again to get our support reaction. Okay, you can do the same thing for your truss. Okay, so how to do that? So now I want to determine AY. So my formula is M0 plus M1 R1. But now I'm not talking about the moments. I will be talking about AY happening at primary structure M0 and AY at solved in your redundant structure M1. Okay, so we are going to gather this data. So let's go to primary structure M0, okay, to see what is the okay, M0. This is M0. Okay, you have determined that it is not that. You have determined that AY is 30 kilonewton. Okay, upward. Okay, then you go to M1. Oops, this is not primary structure, redundant structure. Redundant structure M1, and you look at the AY is upward force 0.5 kilonewton. Okay, so now we can put in our equations. Okay, here M0 is 30 kilonewton upward, M1 is 0.5 kilonewton upward. So you can assume a direction to be a positive side. Okay, for example, I choose going up is positive. Then I start to fill in my equation m0 plus m1 r1. Okay, how to do that? It will be equal to 30 is positive because it is going up. Okay, as what I have assumed here. And then I plus m1. Okay, m1 will be 0.5 going up as well, positive. And then multiply with r1. Okay, which is 105. Okay, so 105. So that you will get this value, 82.66 kilonewton. Okay, we can try for, let's say, Cx. Okay, so for example, Cx, I want to know Cx. So I go to M0, okay, primary structure to get my Cx, and the redundant structure one, M1 to get my Cx. So, okay, in M0, my Cx is 60. Okay, 60 kilonewton going to left. Okay, and then redundant structure, Cx is 0. Okay, so I'm going to put it in my data here. This is 60 kilonewton going to left, and then this is 0. Okay, so now I want to make a sign. For example, maybe I put this as a positive sign, Cx. Okay, so I'm going to fill in the equations again here. Okay, so it will be 60 for M0. M1 will be 0. 0 multiply R, 0. Okay, so now it will be 60 kilonewton. Okay, and it acts according, to the left. Okay, so you have obtained your Cx, you have obtained your Ay. So how about the bending function? Okay, so you can still use this M0 plus M1 R1. Okay, how to do that? Let me show you. For example, now I'm going to determine the bending function for member AD. Okay, so I'm going to put it here. Okay, so the formula is M0. Then I start with M0. 30x minus 15x squared. If you don't know where I get this, I get it from here, M0. Okay, then plus, I follow with this equation plus, and then followed by with this M1. M1 is 0.5 x, and then multiply with R1. R1 I have the value of 105. Okay, so this will be by my bending function for member AD. You can expand it, you can simplify that okay, in a more readable function. Okay, so but this is the process. Okay, so then what if you want to draw the bending moment diagram? Okay, so you can get all these bending function, okay, using this M0 plus M1 R1 for the remaining of this member. Okay, once you get these equations, you can substitute the x value, okay, into this equation. Okay, how you do that? For example, for AV, okay, A and D is here. Okay, so AD is start with A. Okay, therefore x equal to 0 means A, point A. X equal to X means D. So you might want to get more points, substitute different x so that you can plot the curve. Okay, but if you just want to plot the shape, okay, so I think this important point A and D is sufficient. Okay, so how to do that? For A means that you substitute x equal to 0 into this equation, let's say equation 1. Okay, then once you substitute x equal to 0 into this equation, you found that it is moment is equal to 0, which this is true for roller. Okay, roller, pin, okay, so the moment must be equal to 0, okay, and that supports. Okay, then for D, you substitute x equal to 8, okay, in this equation 1, and you will find that you have this moment equal to negative 299, for example. Okay, so let me show you how to draw the bending moment diagram. Okay, so this is I repeat on the important point for AD. This point is A, this point is D, moment at D. So I will start to plot this value into the diagram. Okay, I have prepared here. So A is 0 moment, so I plot it 0. So if you still remember, we cut a section and then assuming the internal moments to act at the positive sign. Okay, meaning that if we consider the left part, this is the positive sign. Okay, if we consider the right part, this is the positive sign. Okay, this positive sign means that whenever you got the moments, okay, you plot at the top part of these elements, positive sign, and at the bottom, negative sign. Okay, so similarly for this right side. Okay, so it also this is for horizontal member. How about for the vertical member? Okay, so you need to decide. Okay, which is the positive side and the negative side. So it depends on how you look it. Okay, so in our previous exercise, if this is a frames, okay, we place our eyes here for this member, and then looking at here, okay, and here. Okay, but for this, how about for this, the structure that you have analyzed? Okay, so actually it is no matter you place your eyes at which side, okay, as long as you understand which is the positive moment and which is the negative moments. Okay, so now in this case, I'm drawing based on the eyes putting here, means that this is the top of my top part of my member, and this is the bottom or down side of my member. Okay, so meaning that at the top upper sides I put a positive, at the bottom, okay, or down below the member I put my moment is drawn in negative magnitude. So now I proceed with this D. So D is negative 299. So meaning that you need to draw it at the bottom of your beam AD. So this is top, this is top, this is bottom. Okay, so I put it here, negative 299. Okay, so next I continue with BD. BD at x equal to 0 is at B. Okay, and x equal to 1 is at the point load. Okay, say point, say Q, I give a point Q here. Okay, so now I have to plot it 0. Okay, and 105 is positive. I brought it up my member, 105.31. So next I go to BD. Still when this x equal to 1, which is at Q, and x equal to 4, it is at D. Okay, so at Q it is still happen to be at the same magnitude, and then at D is 61.2, which is also positive. So you also plot it on top 61.2. Next, okay, on CD. So CD x equal to 0 is at C. Okay, and x equal to 6 is at D. Okay, so now at C we have 0 volts, and at D we have a negative sign, negative 360. So negative will be at this bottom, okay, of these elements will be negative 360. Okay, so now I have placed all the important points bending moment. I need to connect these points, okay, with lines. Okay, so this line normally in two types. Okay, so the first will be straight line. Okay, straight line, okay, will happen, okay, when there is no loads acting on the member. So you get a straight line to connect these, connect 2 points. Okay, so how we know that it is straight line? If you see that span BQ, within this band BQ there is no loads, okay, on the member BQ. Okay, so you can use straight line to connect the 2 points. So now I'm connecting this. Okay, then you go to QD. QD also there is no loads acting on this QD. So you can also join these two point with a straight line. Okay, so this is how you do it. You complete the bending moments diagram for BD. Okay, this is positive. You can put it a positive sign. And then let's move to CD. If you can see that CD also there is no loading at all. Okay, so you use straight line. Okay, so straight line connect these two points, and this is negative. Okay, there is another pattern when your member is subjected to loading. Okay, so we talk here is about UDL. Okay, distributed loading. Okay, either the rectangular or either the triangular. Okay, no problem. Then you are looking at the curve line. Okay, these curve lines we will draw in the concave style. So meaning in such a way. Okay, so either you draw it in this direction, I mean decreasing slope or increasing slope. Okay, to join the 2 points. Okay, and this is concave type. So let's have a look on this A to this 0 to this negative 299. But you need to know that this curve, okay, either it is this pattern 1, pattern 2, pattern 3 that has this inflection point. So we need to know whether this curve, which curve to be used, whether it has an inflection point. So we need to check. Okay, in chapter 1, we can determine the inflection point, okay, by taking the V shear force equation equal to 0. Then we get the X value and substitute this X value into our bending function. Okay, but now we don't have these shear force equations in this page. So what we need to do, we can utilize the bending function. Okay, by differentiate this bending function, you get the shear function. So V is actually equal to dm over dx. Okay, so you need to differentiate the bending function. Okay, so that you get this shear function, and you make it equal to 0 to get your x, and then later after you get the x, substitute this x value into your bending function again. So let's try it. So I have put it here. Okay, I hope you can see my pens. I'm moving here now for AD. Okay, I do not need to find for other member because the other member they of the away reflection. For I have shown here how to obtain the bending function for the real structure, which we use M0 plus M1 R1. Okay, this is the one that we have determined for member AD. Okay, the equation 1 here. Okay, so now this you can simplify it. Okay, this equation 1 I've simplified here. Then I differentiate it. Okay, 82.66x will become 82.66, and negative 15x squared will become 2 multiply negative 15, negative 30x equal to 0. So now from this equation, let's say equation 2, we get x equal to this a value. If it is a reasonable values, so we can confirm that there is an inflection happening at 2.76 meter. So at 2.76, you go back to your 2.76 meter, there will be an inflection point. But what is the value? So you substitute this x into the equation's moment function, which is equation 1 just now. Okay, so you get this is 113.5. Then you can plot it another value here is positive 113.5. Okay, now you can join these three points. So definitely you are looking at this start 3. Okay, or maybe you are talking about joining the first 2 points with 1, and then 2 and 3, and third point with number 2. Okay, so this is how you this is curve, not straight. Okay, so this is how you plot your bending moment diagram. Okay, you can put it positive, and this is negative sign. Okay. Okay, class, do you get what I mean here?
Yes.
Okay, so I will stop this tutorial 7A. Okay, and I will proceed with today's lesson on the arch. Okay. So, I have also shared you a PDF file just now. The other 2 questions that we practice in other class. You can have a look, okay, on that. Okay. So next, I would like to move to my lesson today. Can you see my slides on arch?
Yes.
Okay. So there is a handout in UFuture. You can download that. In that handout, there are 2 arch problems. Okay, but I'm going to highlight only one of it here today with you. Okay, so if you see this problem, okay, we have a combination of arch and beam. Okay, so this arch is circular arch. The description is very clear here. Okay, it is a quarter of this circular arch. Okay, and you need to determine AX. Okay, so first of all, we need to determine how many redundant to be removed. Okay, so we use the equations that we deal with beams and frames. R minus N minus C. Okay, this R, we have dy, we have dx, we have ay, and we have ax here. So we have 4 at total, and we minus 3, we don't have any hinge, we have 1 degree. And since we are going to determine the support AX, we can make this AX as our redundant. Okay, so we can create the primary structure right now. You can imagine now what is your primary structure and how's your redundant structure looks like. Okay, I will show you later. So, but come to here, a revision. Okay, we have been used this before in our previous example. Okay, I hope you still remember. Okay, you use it to determine the geometry. You have used it in your resolve forces as well. So it is a triangular principle. Okay, where you have, for example, your hypotenuse is R. Okay, the length is R. Then you have an angle at this corner theta. So the length, okay, that opposite this angle, okay, you can determine it by using r sine theta. Okay, and the length that close to this theta, okay, you can determine it as r cos theta. Okay, so we are going to use this, okay, to determine some geometry problems in the arch. This is a primary structure and the redundant structure. Okay, so if you can see that here in primary structure, AX has been removed. Okay, so but all the real loads still here. Maintain. So in the redundant structure, no more real load. And we apply back AX or the redundant one with 1 unit force. Okay, this 1 kilonewton. So then you can start to analyze both of these systems. Okay, we need to know how where is our cut section. Okay, so if you're looking at this A, B, C, D, okay, you will see that AB is actually a line, a straight line, and BCD is a curve. Okay, so you the X, okay, that you're going to consider for your cut section will be indifferent. If you still remember, I said the X, please make it parallel with your member. Okay, so therefore, even though A to D in this system is act as one, like one span, because they support at both of the ends. Okay, but analysis with not say splitting, but considering it as two sections. Okay, one is AB and another one is B to D. Okay, where the B to D, the X is running at the curve, and the A to B is running straight horizontally. Okay, so and then we need to know also at each of these section, we are going to cut once. Okay, unless there is some loading that will differentiate this bending function. For example, at AB, okay, we cut once. Okay, for BD, we have to cut twice, 2 times because of this 10 kilonewton. Okay, then you have decided for this 3 cut section. You determine your support reactions, then we can start to get the bending function. So I will show you now how to get the bending function for M0 and M1. Okay, so for M0, let's say I want to start with this cut section 1-1. Okay, I can draw my free body diagram for this cut section. Okay, 1-1. Okay, of course, now I only intend to get my bending moment. Okay, but if axial effect is considered, okay, in this case, okay, then you need to also determine the axial force. Okay, the axial force M. Okay, so you can, but we are not intend to get the end here. Okay, so this is 56.67. Okay, so now I need to know what is the distance, okay, to the cut section. Okay. Okay, if you can see that now I'm at D to C. Okay, member D to C. Okay, and I have put in a range. Okay, at 10 kilonewton, it is acting at 60 degrees from the base. Okay, an angle. So this will be, theta will be talking about from 0 to 60 degree. But please put it in radian. Okay, remember pi is equal to 100. Pi radian is equal to 180 degree. So you can use this to determine if 60 degree, what is the the radiant value, okay, for this range. Okay, so now I want to determine this. Let's say I name it A. So I make a bigger zoom into this triangle, the yellow triangle. Okay, you will see that I'm actually following what we have seen earlier. Okay, when this is R, this is R cos theta, if theta is here, and R sine theta. Okay, so but now the R has value. R is equal to 6 here. So therefore, R cos theta become 6 cos theta, this one. Okay, and of course you can get this value, okay, with 6 sine theta. Okay, but we don't want to get this 6 cos theta. We want to get this A, because I want to know from this 56.67 up to this cut section, what is this A value? Okay, you need to know that this is a circular. So whenever you touch the circle, okay, measured from the central point, okay, this will be the R value. Okay, the R value is equal to 6 meter now. Okay, so therefore this A must be this 6 meter minus this 6 cos theta. Okay, this case will happen, okay, at any locations, okay, in this curve. Okay, so no matter this is for example, in whether this theta is 10 degree, whether this theta is 20 degree, 30 degree, 40 until 90 degree, this template, I would say, is the same. Only you substitute the different theta into this equation. Okay, so we will have a look later again on this page. Okay, but now we already obtained the A. A is equal to 6 minus 6 cos theta. Okay, so A is equal to 6 minus 6 cos theta. So the moments here will be the loading, 56.67, and multiply with the distance. Okay, that's all, your moments. Okay, and it is positive because it is acting oppositely, okay, to the internal moments. Okay, so I'm going to move to CB right now, cut section 2. Okay, for CB, this is C, this is B. Okay, now this will be from 60 degree to 90 degree. Okay, so but you put it in the radian. Okay, so I'm going to draw a free body diagram for you on this case. Here we have again 56.67, and we also have a 10 kilonewton, and we have a cut section here. We already know what is this value. How? Just look at this yellow triangle right now. If you can see that this yellow triangle, the theta is now greater angle compared to our section 1 just now, but the equation is still the same. Okay, if you can see that this is R, 6 meter, and the base must be 6 cos theta. And this, now if this is still A, okay, therefore this is still 6 minus 6 cos theta. If you can see that there is, the template is still used, even though this triangle more how to say shallower depth of this triangle compared to this higher depth of this triangle. The template still applied. So now we can know that this A is equal to 6 minus 6 cos theta. Okay, now I need to determine this value. Let's say B. Okay, how to do that? We already have this information, 6 cos theta. Okay, we already have this. Okay, again, I draw it here. Okay, 6 cos theta. Now, if I draw another triangle that we know the angle is 60 degree. Okay, so again, let us find what is this length. Okay, it must be, class, are you able to help me? What is this? What is this length?
Cos theta.
Yes, 6 cos.
60.
Cos what? 6 cos 60. Yes, because we know that this angle is 60 right now for this green triangle. So you have 6 cos 60, and you have determined 6 cos theta here. Okay, so this will be the B. B will be here. Okay, how to get the B? You must have 6 cos 60 minus this 6 cos theta. Okay, I can't draw it for you right now. Maybe I put a circle. Now this is B. Okay, so to get the B, you must use this value 6 cos 6 theta minus the 6 cos theta. Okay, so therefore B will be 6 cos 60 minus 6 cos theta. And this 6 cos 60, okay, you get 3 meter here. Okay, so now the bending moment we can get, we can determine right now. Okay, so for example, 56.67 with the its distance is 6 minus 6 cos theta. And we have 10, which is acting the same direction, therefore is negative 10. Multiply with 3 minus 6 cos theta. All right, you solve for your bending equation for this section CB. Then you can proceed with section AB, okay, which your x start from here, from A. Okay, you have 253.33 with the distance to the cut section is x. And you also have UDL, which you can represent in the point load 10x, which is acting halfway, x over 2. Okay, so let's just quickly find the moments here. 253.33 33x minus 10x x over 2. Okay, so you solve for M0 right now. Okay, let us move to M1. Okay, you found that the cut section 11, cut section 22, the moments will be the same. Okay, because there are no there is no any loadings that differentiate these moments. So now I will get the moments here. If you can see that this 1 kilonewtons will be contributing to the moments, and 2 over 3 as well. Okay, so 2 over 3 again the templates, if you can see that, subjected to this. So I have put it 2 over 3 and the distance is 6 minus 6 cos theta. And then 1 kilonewton, what is the distance, the vertical distance? Can you help me, class? Thank you. This is 6 sine theta. So you have 1, which is acting the same direction, so you have negative, multiply with the 6 sine theta. All right. You don't confuse with this. This is not our moments. This is the cut section 2. Okay, so this will be your bending moment for cut section 11 and also cut section 2. Okay, and then we left another one here. Okay, which is still with this value AY only. Okay, so it will be negative 2 over 3 x. Okay, the distance is x. Okay, so once you have determine this moment function, you can put it in the table, okay, and then you can start with this compatibility equation. Okay, please, you must be able to write this right now, okay, even for different of d. Okay, so now since we have d equal to 1, we have only one equations. Okay, this is delta 1. So now let us have a look on how to fill in at least one of these delta. Okay, if you still remember for beam and frame, we are using mm over EI dx. You need to check this A, B, D, C, CB, whether the EI is constant. If not constant, you need to put it in your table so that to remind you, okay, when using this compatibility equation, you don't forget about this difference of EI. Okay, and if you still remember in chapter 1, when we're dealing with arch, okay, and when we are dealing with theta instead of x, okay, we use the integration m over EI r d theta. Okay, you have another details to put in this integration. So the r. So if you look at DC and CB, which you deal with this theta, you have r here. Okay, so let's try on member AB. Okay, AB, the range is 0 to 3. Okay, and we have M0 here. You have M1. Okay, so then we move to DC. We have a range 0 to pi over 3. Okay, this is M0. Okay, and this is M1. Okay, M0 and M1. And don't forget about this R d theta. Okay, then we move to CB. You have pi over 3 over 2. Okay, this is M0 and this is M1 and you have R d theta. Okay, so class, I want you to try using calculator. After my class, please try manually. Okay, but now I want you to try using your calculator to find this result only, this part only. Okay, so I show you my another more detailed expand equation. Okay, so where I multiply the 6, okay, with this 56.67, okay, and multiply into this bracket as well. Okay, then I get this statement of equation. Okay, can you help me to find this using your calculator, whether you can get this value? Okay, be careful on this bracket. Okay, and in my calculator, when I would like to insert on this theta, I put alpha x. Okay, so I will give you about 3 minutes, okay, to try whether you can solve this using your calculator. Okay, class, do you understand what my request?
Yes.
Yes.
Okay, so
Yes,
I wait.
ma'am.
Yes, 3 minutes. Okay.
Yes.
Yes.
Have you determined the value, class?
Yes, I get it.
Okay, how about the, okay, fine. So for those who haven't get the value, don't give up. Okay, you have time later. Okay, because I want to continue with my lesson. Okay, so can I get your attention back, class?
Yes, madam.
Okay, yeah. So now we have know the steps how to solve this arch problem. Okay, so at at the final stage, you shall be able to get this solving this equation, compatibility equations. You shall be able to solve your R. Okay, this R here, please, I need to remind you again and again. You need to know what is R means. This R is the redundant that you have removed earlier, which means in this case is AX. Once you solve for AX, you can solve for remaining support reaction and bending function, remember, just by using this M0 plus M1 R1. Okay? So then, I have to show you a few tricks here, okay? If you see your WhatsApp group, I have shared this handout with you. Okay, there are two examples on the arch. Okay, that I would like you to study after my this explanation. Meaning that after my brief, this lecture this afternoon, the remaining time I want you to read. Okay, that two examples. Okay, make sure you understand. Okay, you can redo or you can just study first. Okay, and find out what is the problems that you don't understand. You can post it to me in the WhatsApp group. I will reply. Okay, what does this mean? And just to answer, okay, your question. Okay, now before you left for your reading, okay, I would like to highlight this reflective symmetry. Okay, this reflective symmetry principle is very important if you are dealing with a symmetric structure. Okay, if you apply this reflective symmetry principle, you may, okay, most probably save your computational time, and you may also reduce your redundancy. Okay, if you can see that flexibility methods, if you have more redundancy, your process become longer. Okay, so by using this reflective symmetry, you can have these benefits. You need to make sure it is a symmetry structure first. So how to classify or observe it as a symmetry structure? You can see it in a few forms. For example, in terms of geometry or the dimensions. Okay, in terms of the supports, condition, pin, roller, fix. Okay, and in terms of the loadings. Okay, all these must symmetry. Means that when you define a mirror line or central lines, okay, for example, in this case, it happened to be at B. Okay, so if you have defined this central line, you found that the left part and the right part, it is just a mirror. Okay, so you need to make sure it is mirror in terms of geometry, the dimensions. In terms of the support, like for example, A is pin, C must be also pin. It cannot A is pin, C is fixed. No. Okay, and in terms of loading, okay, it must be symmetry. Okay, for example, here, 10 kilonewton or 100 kilonewton, let's say at a certain point of X. Okay, so come to here, 100 kilonewton also acting at the the mirror, at the mirror side. Okay, so you need, once you have found that this is symmetry, okay, you can use half of the structure, okay, either left part or right part to analyze this system. So instead of the whole system, you analyze it. Okay, you only analyze half of it. and this result will be applied to the other half. Okay, you need to do some treatment to this half structure, okay, at the mirror line or central line, so which is happening at this B. Okay, so how you do that? You put a slider support. Okay, then you simulate, okay, the whole system. Okay, so the slider supports, the support reaction is this is Bx and also Mb. Okay, so maybe in this case it doesn't seems like it has reduced any redundancy here. I will show you. Okay, for example, this D for this the full structure is R minus N minus C, which is 4 support reaction minus 3 equal to 1. Okay, in this half structure, after you apply this reflective symmetry principle, this D is equal to still 4 minus 3 equal to 1. So it doesn't seem you have reduced any. But if you have fixed support at A and fixed support at C, say okay, so I recalculate the D. When it has a fixed support at A and C, you have 6 support reaction. Okay, at total you have 3 degree of indeterminacy or 3 redundancy to be removed. Okay, and for this half, okay, half of this circular arch, okay, you will have 5 support reaction minus 3, you have 2 degree of indeterminacy. So you can see that you actually have removed one of the redundancies in these systems. Okay, it makes your calculation easier right now. Okay, and if you notice that these 440 kilonewtons, when come to this reflective symmetry calculation, it becomes 220 kilonewton. This is because this point load is acting at the mirror line. Okay, when it is acting at the mirror line, you need to split it into 2. One, half of it to the left part and half of it to the right part. Therefore, only 220 kilonewton it should be placed at B for your this reflective symmetry geometry. Okay, but if you have 100 kilonewton in your system, okay, here at the X from A, you will remain 100 kilonewton. Okay, because it is not acting at the central line. Okay, so this is the first thing I want to share with you about the beauty of reflective symmetry, and you will use this also in the stiffness method later. Okay, so I have another thing, two more items to share with you. Okay, so this is about a circle equation, or I would say also a theorem Pythagoras, okay, on the x, y, and the r. Okay, how you get this r? You get x squared plus y squared equal to r squared. Okay, so now I'm going to refer to the problem again. If you notice that in this problem, we do not know the r value. Okay, in our previous slides, okay, we need the r to know to solve for some of our lengths. Okay, so in this case we also require r value, but this r value definitely not here. Okay, if you by observation you will know that the center of the circle will not be this at this x. Okay, so it might be some way down here that we do not know where, and we need to find it. Okay, so now if you refer to the star, the illustration that I show here, okay, we can apply this equation, x squared plus y squared equal to r squared. Okay, using this purple triangle. Okay, and this triangle, where is this triangle? This triangle is actually, if you have this O, let's say this O is your central point of the circle, and you do not know where, okay, you can connect this A to O, okay, which this will be also your radius because this is circle, okay, so you can create a triangle here, okay, and this O must be acting at the center, okay, at just down of the B, okay, then you notice that this X is actually half of this 30 meter, okay, because B is acting at the center, okay, so this will be 15 meter. Okay, next we want to know the Y in order to get the R. If you look at this statement, this equation 1, let's say, we have X, Y, and also the R. Okay, now we need to know, make known Y before we can solve the unknown R. So how to get the Y? Okay, you will know that OB is also R. Okay, because B is at the circle and O is a centroid. Okay, so O to B is also R. Okay, and we already know that, okay, A to B, the height is 4.6. So therefore, for Y, it will be R minus 4.6. Okay, so you can put in the X value, Y value. Okay, then you solve for your R. Okay, so I have to point out this, if you have encountered such problem that you need to use the R to find the geometry, but you don't know how to get the R. Okay, so the next things I would like to share with you is in your handout. Okay, so later when you open your handout that I shared today, you will see there are two problems. One is problem 5.10 and another one is the one that I shared with you just now. Okay, problem 5.11. Okay, so I choose this 5.10 because this is quite an interesting structure. Okay, and they are something that I want to highlight here. Okay, if you look at this, this is a frame. Okay, frame. Normally, we talk about bending moment. Okay, but you need to remember, frame also has axial force. Okay, maybe not common. Okay, but beam can also have axial force. Okay, so whenever they have axial force, they will have axial deformation, okay, or axial effects, okay, in their behavior. Okay, so therefore, if you are asked to consider the axial effect, maybe it's not that significant compared to moments bending effect in the beams, frame, and arch. Okay, but if you are requested to do that, you need to also determine another axial force. And okay, why I say so is because in this problem, if you can see that EA is given to you. Okay, you need to know that EA is used in to get the deformation for the axial effect. So N and L over AE. Okay, so in this case, and then some more is the temperature in member CE rises of 30 degrees Celsius. So this is also deal with your N, okay, temperature influence, okay, in your structure. Okay, so these are something that I would like to highlight here. Therefore, when you read this problem, you don't get shocked, okay, because they have considered both the bending and also the axial effect, okay, and they need to determine the axial force for this frame. Okay, if I scroll down, Okay, and then I would like to also inform you on this F. Okay, don't worry about this F. This is only a symbol. Okay, F means here the exophores. Okay, big N and small f is a small n. Okay, and I think the remainings I think is common. Okay, I mean you have used it before. Okay, so before I leave you for your reading assignment, let me check your attendance. Okay, so let me check your attendance first. Is it this one? Okay, Siti, Najiha, are you here with us?
Yes, madam.
Yes, madam.
Okay, can you take your attendance? Maybe I will stop recording for now. Okay. Okay. Oh. Okay. Let me go to another class. Okay. And will be very small to you. Maybe I will just copy and paste in here. That's fine. Announcements. Okay, one of it is, so I think this nothing to be so serious of other tests yet. The correction is this one only. Okay, test 2. I think in our earlier date is 11, so it is not 11, it is 18 December of this year, 18 December, but the week is still the same, week 9. Okay, so this is 23 marks, huh? Am I copying wrongly? Yeah, now this is 23 marks. Okay, the remaining tests are 20. Okay, so okay, so you have another about 70 marks to get, right? So if you feel like you're not doing well in your first test, so why not? Okay, we work hard for this another 3 tests. Okay, so this is the announcement, okay, posted by the coordinator, and we really overlook on this week 9 is actually 18. So next is my announcements to you. Okay, so this is 18. I'm sorry, it's just corrected. Okay, and then for this preparation, for this test too, I want all to work in a group of 5 students, the group that you have formed earlier. Okay, the task given to you is you need to prepare for an oral presentation. Okay, the group leader, please you can start coordinate. Okay, distribute the task, okay, to each member. Okay, so that they can prepare for the oral presentation, which will be scheduled in the second class of week 8. Okay, so next week is a semester break. Okay, then we will start with week 8. Okay, week 8, not the first class. The first class will be on the composite structure, and the second class will be on the for this our provide a session for this oral presentation. And what you need to do is you need to solve for these 4 questions. Okay, you will realize that the 4th question on beam is cannot remember. I think the students need to use other methods to solve for it. But please, okay, use flexibility methods to solve for this question. Okay, question 446F. Okay, you can download this from UITM library. Okay, on this past year question. Okay, you might not be able to solve this yet. Okay, but please try. Okay, so the format of the presentation, this is wrong. It's not me, it's Teams. Okay, oral presentation in Teams. Okay, you'll be given about 10 minutes and you will be the one to control the screen. And please just talk about the PDF. I mean the solution in the PDF file. No need to be so beautiful, the slides, no need. Okay, I just want to comment on your solution, but make sure it is clear, okay, so that everyone can see it, okay. And then there will be a Q&A and feedback, okay, for your solution. Okay, class, do you understand what you need to do?
Yes, madam.
Okay, yeah. So I have to stop right now. Okay, you can proceed with your reading assignment. And I wish all a happy holiday, happy semester break. Okay, and then stay safe and don't go to somewhere very crowded. You know, the cases are increasing right now. Okay, so I see you in week 8 later.
Okay, madam. Thank you.
Okay.
Take care, madam.
Okay, yeah.
Thank you.
Thank you, madam.
Thank you, madam.
Madam.
Thank you, madam.
Thank you.